We now want to see how to apply the concept of the conservation of angular momentum. So to introduce the principle in example form, we're going to look at a star system, a particular star, and initially the star is going to have a radius of 1 million meters, which is actually on the smallish side for a star. And we're going to consider that it is rotating once every 10 days. The sun, for example, rotates every 28 days, plus or minus a few hours. So this is at least on the order of typical rotations of a star, but we're just going to keep the numbers nice and neat just for the sake of example. Now, one thing that can happen to stars, in fact, not a star this small, but for larger stars, what can happen is they go supernova, and a lot of their outer material gets ejected off of the star, leaving them with just a very dense nuclear core, what we call a neutron star. So in this example, we want to see what the rotation rate or the angular velocity of our neutron star is. So if we start out with a very large star and then it puffs out its outer layers and all we're left with is the dense core, what is the rotation rate of that star if its initial radius is 1 million meters and it has a rotation rate of 1 revolution per every 10 days, all right? And the assumption we're going to make is that the mass of the leftover neutron star is essentially the same as the mass of the initial star itself. Yes, some of the matter gets puffed off or blown off, but the amount of matter is fairly insignificant in true physical star processes, stellar processes. The overall mass of the neutron star is usually very, very close to the overall mass of the original star. So we're going to consider no mass loss. So how can I determine what the final angular velocity is going to be in this case? Well, we start with the principle of conservation of angular momentum, which states that the initial angular momentum in my system must equal the final angular momentum in my system, even if some process has occurred. Now, the caveat here is this process, or the conservation of angular momentum principle, holds in the absence of no external torques, okay, or in the absence of external torques. If I have no external torques acting on my system, then I can apply the conservation of angular momentum, okay? If I have external torques, then I cannot apply the conservation of angular momentum. Okay. Now, in this particular process, yes, the star is going to have some of its outer layers blown off, but all of that is internal to the system, and as long as the collapse is spherically symmetric, then at least this will give me a very good approximation of what would actually happen in a real star. Okay, and we'll see that our results are actually it gives us a good ballpark number for actual numbers for real neutron stars, which is a really cool result. So, how can I set up the principle of conservation of angular momentum in this case? Well, my initial angular momentum is going to be given by my initial moment of inertia times my initial angular velocity, and this is going to be equal to the product of my final moment of inertia and my final angular velocity. And hopefully you can see that if this product is to stay constant, then if my moment of inertia goes way down, then my angular velocity should go way up in the final case. And my moment of inertia should go way down. I have a same amount of mass, but a much smaller sphere. And here I have a much larger mass and well, I have a much larger radius, okay, same amount of mass, but it's a much larger radius over which that mass is distributed. And so my initial moment of inertia is going to be much larger than my final moment of inertia. So if this product is to hold, if this has gone down, then this must increase in proportion, okay? So recall that the moment of inertia of a sphere is 2/5 mr squared, and I multiply that by the initial angular velocity. And so my final moment of inertia is going to be 2/5 m times my final radius squared times my final moment of inertia. And we see that my 2/5 can cancel out, as well as my m's. And we're left with my final radius squared times my final angular velocity. Okay? So now if I want to solve for omega f, it's a relatively simple procedure. Omega f is simply going to be omega I times the square of the ratios of the initial radius to the final radius. Okay? And this is 1 revolution per 10 days. We'll write it like this. And then this is going to be 1 times 10 to the 6th meters. And this is 1 times 10 to the 3rd meters. Now, let's let that sink in for a moment, okay? My initial radius is 1,000,000 meters, okay? And that's actually quite average for a star, okay? That's not that big for a star. The Earth is 6,000 kilometers, for example, in radius. And so for a large star, this is hardly anything at all. This is a relatively small star, okay? But look at how large the radius of our neutron star is. This is a typical radius for a neutron star, or order of magnitude for a neutron star, on the order of kilometers. Not much larger than an actual city, okay? So you're taking something as large as the sun, and then all of a sudden its mass is collapsed down into something the size of a city, and that is a phenomenally dense object, okay? And that's where these phenomenally high rotation rates come from, because you're taking essentially the same mass, spinning at a very slow rate, and then cram all that mass down into a very small area, or volume really, and so it must spin at a much higher rate. Okay, so if and this needs to be squared, right? So if I look at 1 revolution per 10 days, and then I have 1,000,000 meters divided by 1,000 meters, this gives me 1,000, and then 1,000 squared is another 1,000,000, and 1,000,000 divided by 10 is 100,000. So what this is telling me is that my final rotation rate is 1 times 10 to the 5th revolutions per day. 100,000 revolutions per day. Now that may seem extremely surprising, that even something the size of a city can rotate that fast. Now, how many revolutions is that per second? Well, there's 86,400 seconds per day. So if I divide this by 86,400 to put this in revolutions per second, it's really close to 1.15. And that's an astonishing number. And as a point of interest, that is actually a typical value of what we would observe for neutron stars. Neutron stars orbit on the, or I shouldn't say orbit, they rotate at approximately the rate of fractions of a second to a few seconds on average. So this is definitely in the ballpark for an actual rotation rate for a neutron star. And we got it from the principle of the conservation of angular momentum. And for every conservation of angular momentum problem, you should start right here, right? Recognize that the angular momentum before your system and after your system must stay conserved, okay? Hope you enjoyed the video. We'll see you next time.